In this module, we are going to continue with induction and use another application of it in the context of recursive definitions. So here we are going to define recursively defined functions. So a recursive or an inductive definition of a function consists of two steps. The first is the basis step, which is where you specify the value of the function at 0 or the smallest number where the function is defined. Sometimes the basis step would involve more than one assignment, and we will see why that is necessary sometimes. And then we have a recursive step where we have a rule to find its value at an integer from its values at smaller integers. In other words, you might define the value at 5 in terms of 4, 3 and 2, etc. A function fn is the same as sequence a0, a1, a2, a3, where f of I is equal to ai. In other words, f of 0 is the first term, f of 1 is the first term, f of 2 is the second term, and so on. Remember that this is exactly what we used to relate functions and sequences to each other. So let f be a function that is defined recursively as follows. Let's say f of 0 is 3, f of n is 2 times f of n minus 1 plus 3 for n greater than or equal to 1. Note that these two rules together define the value of the function for all non-negative integers. So if the integer is 0, we use the first rule. The integer is 1 or higher, we use the second rule. So let's say we want to find f of 1. So here we can see f of 1 is 2 times f of 0 plus 3. F of 0 is defined as 3, so we substitute, so it's 2 times 3 plus 3, that is equal to 9. We can compute f of 2. For that we will need to do 2 times f of 1 plus 3, and that will give us the value 21. We can continue. I would ask you to check the math yourself, but f of 3 will come out to be 45, f of 4 will come out to be 93, and so on and so forth. Let's look at one more example that is more familiar. Here we are going to define the factorial function recursively. So factorial function is f of n is equal to n factorial, which is the product of the first n numbers. So we can define this inductively or recursively as follows. We can say f of 0 is 1, 0 factorial is 1, and we can define f of n to be f of n minus 1 times n. Now here we want to do something opposite. Here we have a sequence an is equal to 2n plus 1. This is not recursive because an is not defined in terms of a of n minus 1. However, we want to make it into a recursive definition. So we can see that if an is 2n plus 1, a of n plus 1 is, we can substitute 2 times n plus 1 plus 1, and that means we can write an plus 1 minus an is equal to 2. That means we can write this as a recurrence relation or a recursive definition that says a of n plus 1 is equal to an plus 2. In order to make this definition work, I have to define one initial value. In this case, a1 is equal to 3 because that is something I can derive from this equation. The Fibonacci numbers are recursively defined as follows. The first term is 0, the next term is 1, and the subsequent terms are obtained by adding the two previous terms. So let's find f2, f3, f4, f5, etc. So we can substitute. f2 will be f1 plus f0, that will be 1 plus 0, that is 1. f3 would be 1 plus 1, that would be 2, so on and so forth. Check the math, make sure that you understand how we are computing these things. An important thing that we have over here is, in order to find, say, f of 1000, it's going to take me some time, but another issue is, in order to do that, I have to compute what is f of 999, f of 998, and so on. One of the things we are going to study a little later is if we can find closed form solutions for this. That is, instead of having to find all intermediate values, we could simply plug in the value of n and get the value that we want. Note that here we have used an alternate notation, f subscript n instead of f with parenthesis n, which is what we normally use for functions. For sequences, traditionally we have used n as a subscript, and we will use these interchangeably because they essentially mean the same thing. We can define sets recursively as well. So for a recursively defined set, we need to have a basic step that specifies a few elements in the set, and a recursive step that says how we get new elements in the set based on previously defined elements. We can have exclusion rules, basically, that says the only elements that are in the recursively defined set are those that have been identified by those two rules. Anything else is not going to be in the set. Here is an example of a recursively defined set. So here we have a basis step that says 3 is in the set, and we have a rule that says if I have x in the set, y in the set, then x plus y is in the set as well. So we can find a few elements in the set. So if we have 3 plus 3, that's 6, 3 plus 6, that is 9, 6 plus 6 or 3 plus 9, that's 12, and so on and so forth. This is another example of recursive definition where we want to define strings. A string over alphabet sigma is any finite sequence of symbols from sigma. So let's say if we have the alphabet to be all the letters on the keyboard, then we will have some strings like A, B, F, E, D, 1, 1, 0, 0, 1, and so on and so forth. We can define strings over sigma in recursive fashion as follows. We can say the empty string is a valid string, and then we can define recursively where if I have W as a string that is in S, X is the alphabet, then I can get WX that is going to be in the set of strings as well. So if I take sigma to be 0, 1, essentially I'm going to get the empty string and all binary representation of different numbers. Once again, we have reached the check before you go ahead slide. So what I want you to understand here is the relation between recursive definitions and mathematical inductions. In recursive definitions, we have things like f of n is defined in terms of some previous f terms. Now, if I want to prove some property about f of n, like f of n is a particular function, then I can do this inductively, where I'm going to assume that these properties are true about f of n minus 1 and f of n minus 2, and then based on that, go ahead and prove the corresponding property. In this case, the basis case would be the scenario where f of n is defined without recursively. So essentially, in case if this was a Fibonacci sequence, it would be the values of the first term, the second term in the sequence.